I had a student email recently that somehow made it past the spam filters. And it asked a couple of questions as we do our groups and integration work. And as I read the question, I thought, I bet you more students in the class could probably benefit. And so my solution was to, in a class of crappy videos, make another crappy video. Now, of course, when you're teaching an online summer class, you're supposed to be able to have plenty of time to think about other important things and advancing the field. But I decided to go ahead and tackle the question because I thought it'd benefit a number of students in the class. One of the questions was simply this: is it possible for two different structures, to have the same number of groups of protons, same number of groups of carbons, and the same integrations? And the answer to that is, it is certainly true. It is certainly possible that that can happen. So I thought about it for a moment. Here are two nice example molecules, and I'll show you the spectra of these molecules in just a moment. One of them would be this, okay, a simple molecule, dialpha ketone. Now, the other one, similar in structure, that I'm going to use is this. I'm going to put two chlorines in these positions. Now, this one, 3,3-dichloropentane, this one, diethyl ketone. If I asked you to analyze how many groups of protons, how many groups of carbons, what would the proton integrations be, I would hope all of you fairly readily would be able to come up with this. That this molecule has 1, 2, 3, 4, 5 carbons, but oh, look at that little axis of symmetry. And so it would have 1, 2, 2 hydrogen groups. And it would have 3 carbons to show up in an NMR spectrum. And the hydrogen groups would be, well, there are 3 here, 2 there, mirrored on the other side, 3 here, 2 there. And so some of you might report a 3:2 integrated ratio. Others might report a 6:4 integrated ratio. Either one is perfectly acceptable for me. Remember, 6:4 is the actual number, but the symmetry, 3:2 is probably what you'll see on the spectra because it uses the smallest whole number ratio. For this particular molecule, we look at it carefully, we notice it too is symmetric right down the middle. And it has 1, 2, 3, 4, 5 carbons, but the symmetry is going to lower that. We have a group of 3 and a group of 2 protons, so we have 2 proton groups once again. We have 3 carbons, okay, because these two are mirrored on that side. And if we count up the number of protons, well, there are 3 here, 2 there, mirrored on the other side. Once again, a 3:2 smallest whole number ratio, 6:4 actual number. Pick either one, it doesn't matter to me. So here are 2 molecules that are going to, we would expect, give very similar results. So here are the proton NMR spectra for these 2 molecules. And what I've done is I've stacked the 2 structures on top of each other and scaled them so that they have exactly the same values on the left and on the right. And you can see they do look very similar. There are indeed 2 proton groups. They do indeed integrate to a 3:2 ratio. The one critical difference between the 2 are the chemical shifts, where the peaks are, exactly what value on the axis are these peaks. Now, we have not talked directly about chemical shifts much yet. Oh, we're going to, but we haven't gotten that far yet. So we're concentrating at the moment only on the groups and integrations. But indeed, the 2 spectra look remarkably similar to each other. If we switch over to the carbons, we see exactly what we would expect, 3 carbons for each of these molecules. Here, the chemical shift difference is much more obvious, and we will make a great deal out of the chemical shifts, especially of carbons and carbonyl groups, as we move along in the course. But there they are, the proton spectra and the carbon spectra of these 2 molecules indeed are very similar to each other. The only significant differences are the chemical shifts, which we get to later, coupling patterns, the triplets and the quartets in the proton spectra. They are also very similar, and that's something we get to later in the course. So indeed, the answer to the question, is it possible to have 2 molecules with different structures, but the same number of groups of protons, carbons, and the same proton integrations? Answer is yes, it is indeed possible. That sometimes will lead to a follow-up question, and that would simply be, okay, how do you tell the difference between these two molecules? And the answer is the chemical shifts will help you quite a bit. But to really nail it down, and I must admit, it pains me to admit this, but we have to take into account the fact that there are other methods, other forms of spectroscopy we could do to help tell the difference between these two spectra, especially since their proton and carbon NMR spectra are very similar to each other. A couple of ideas that come to mind. The mass spectra result, the molecular weight. This molecule has a molecular weight of 86 grams per mole, where this molecule has a molecular weight of 141 grams per mole. And so a molecular weight determination, perhaps a mass spectra, would get us this information and allow us to tell the difference between the two. I'll even concede that infrared spectroscopy would play a role here as well. If you recall infrared spectroscopy, carbonyl groups are among the most prominent and distinctive groups you see in IR. This thing should have a large peak somewhere in the neighborhood of 1800 wave numbers. That's a distinct position for ketone carbonyls. Down here, no carbonyl group. Carbon chlorine, carbon halogen bonds are also relatively distinct, somewhere in the neighborhood of 700 wave numbers, and that could vary quite a bit. But those are two things you could do to try to tell the difference between the two molecules. Either mass spectra results, IR results would be helpful here. The chemical shifts in the carbon spectra are also where NMR really shows a strong difference, and we'll get to those chemical shift differences later. The second question was, is it possible to have a molecule as a structure that integrates only to one? And yeah, that would be a very simple molecule, but again, I'm going to give you a couple of the possibilities. This is one example. If you look at the proton NMR spectrum of this thing, you're only going to see one peak. And when there's only one peak, the default is to simply, if you integrate it at all, it's going to be assigned a value of 1, simply because there is nothing to compare it to, no other peak to get a ratio. And so it will have a value of 1. Another molecule that would feature that type of thing happening is this ether, okay? Dimethyl ether. This one, symmetric molecule, and so these two methyl groups are going to be equivalent to each other. They're going to give 1 peak. And with no other protons in there, you're going to get an integration. If you even bothered to integrate, it would simply be assigned a value of 1. And so once again, here the integrations would simply be 1, this one representing a methyl group with 3 protons, this one representing 2 equivalent methyl groups totaling 6 protons. Sometimes really, really simple molecules are a little bit difficult to handle in NMR because it does not give you a lot of information. As you'll see as we move along, it's when you get into molecules with a number of distinct groups of protons and carbons, then the information flow really begins when you're studying NMR spectroscopy. So there, good questions. Keep them coming. Hope this was helpful. Talk to you later.